Okay. Okay. All right. So I think we're in the right page now. So welcome everyone. We're in the introductory work. This is the introductory workshop for 3D UTAPWELS by Bruce, Roger, and me. So the first thing is, what is UTAPWELS? So 3D UTAPWELS is the University of Texas at Austin Petrophysical Well Log Simulator. That's what it stands for. And it's basically the software that is developed by the consortium, the joint industry academic formation evaluation consortium at UT Austin. And what it actually does is, in a few words, and this is our mantra, is the software is a software to construct an accurate Earth model that is petrophysically consistent and in agreement with all measurements. Why? Well, because we want to have an accurate formation evaluation. That's the main goal, is to have as accurate as possible formation evaluation. And we do that again through a single Earth model that is petrophysically consistent and in agreement with all measurements. Now, we like to see it as a Sudoku analogy. In Sudoku, I don't know if you guys ever played that game, but the way it works is you have this is how it starts. You're given certain numbers in this grid. And those numbers are equivalent to the information that you get when you're logging a well. You can get the resistivity logs, you can get core data, sonic logs, all that. And then in Sudoku, you're trying to find those red numbers that follow certain rules. So in our case, those red numbers are the Earth model that you're trying to figure out. And you try to figure that out because the formation evaluation is going to be a lot better if you have a solid Earth model. And there are certain rules that you need to follow so that Earth model is solid. In Sudoku is that, well, the numbers cannot be repeated in a line, cannot be repeated in a horizontal line or in each of the boxes. For us, is all the petrophysically consistent rules that we have. That means that all measurements are going to honor the model that connects them among each other. So that means Archie has to be consistent. That means the effective medium theory needs to be consistent. The mineralogy needs to be consistent, all that. And at the end of the day, we want to make sure that we get the porosity right, that we get the water saturation right, and that we get the hydrocarbon pore volume right. That's the bottom line of what we're trying to do. And then a typical example of why you would prefer to do modeling through UTAPWELS instead of just using logs is because imagine you have a scenario where you have a resistivity measurement, and then the way you're going to do interpretation traditionally is just you're going to say, okay, there's three layers here, and these are the three different values. But if you run a simulation, you're going to see that the tool response for that interpretation that you gave would have given sorry. Okay. So the interpretation that you would have used would if you run a simulation would give you a very different tool response than what you actually measured, which means, of course, that the interpretation would be wrong, and UTAPWELS is going to help you correct for that. It's going to tell you, well, actually the interpretation that you need to give it is that the resistivity is significantly higher. And if you run the simulation, you see that the tool response actually matches the field log that you had. This is a typical example, and it can be expanded to other things. And there's many other reasons why you want to use UTAPWELS, but that's one of the key ways, or the key reasons, I should say. Now, when you open the software, this is what you're going to see. You're going to see a database tree in the left. You're going to see a quick info panel. If you select any of these logs or any of the data that you have in this data tree, is going to have some quick information here, the average and so on. And then in this bigger window, you're going to have either the welcome screen, which is what you're seeing, or a plot, or the CSF, which stands for Common Stratigraphic Framework. That's the fancy word we use in UTAPWELS for the set of wells and formations that you have around the well. So this is you would have a full 3D visualization of the wells. And of course, you have the menus. You have the project menu where you can save, load the typical things that you would do. You also have project notes if you want to add notes to the projects, any specific extra information you want to have there. Then this menu is relatively new. We have a multi-well menu where we have access to modules that apply to all wells simultaneously. So the crossplots and the multi-well quality control are plots that are going to be capable of handling data from multiple wells. And then the databases and some of the the databases and the models. Basically, these are the models. They are all related to the rock classes. Then we have the settings. Well, they'll become more relevant when we actually use it. And we have help. Help is actually very useful, very helpful, let's say. There's access to all the extra folders that you may want to look into. For example, this data sim folder has all the information, all the files that were used to run any simulation are going to be there. So some people like to see the information a little more detailed. They can go in there. You can manage your licenses, and you can get a little more help. Then, other than the main window, the other window that you would be using more, in fact, the window that you're probably going to be spending most of the time on, is the well interpreter. So for each well, you're going to have a window like this that handles each well, and you have all the information to save and load. You have same multi-well access, and you have other menus that are specific for the well. One of them being the Earth Model Builder. It's a set of modules that allows you to modify the Earth model. We'll talk a little more about exactly how the Earth model is defined in a little bit. Then you have some modules that allow you to manipulate logs. We'll also go into them a little bit. We have all the simulations, access to the inversion modules, and to the Pore level petrophysics. That it's so we have an extra sub module where you can do Pore level petrophysics. We have not developed it much in the past 2 or 3 years. At some point, it seemed like there was going to be more interesting in it, and we worked a little more, and it's been a little stagnant, to be honest. So if you have any specific questions on that, we can talk about them, but we don't have anything planned on that. Then at the very end, you have the unit system. You can modify it here, and we have snapshots, which we can talk about it in a little bit too. Again, if you have any questions or comments, go ahead at any point. Now, besides the well interpreter, in the well interpreter is where you're going to be able to import data and manipulate it. Like I said, this is one of the places where you're going to be spending most of your time. You have the track display that, of course, allows you to plot all the logs and the Earth model. You can modify the view. You can modify the plots that you're going to be using. We work with something called mnemonics and templates. We'll go into a little more detail during the presentation. But all you need to know about this one for now is that we've tried to really make it as user-friendly as possible, so that you don't have to spend too much time plotting, because that's how it used to be. So we really tried to simplify that, so that when you work with multiple projects, you don't have to redo the same plot again and again and again. So this is more directed to George and the people that have been using it for a while, Hesham. These are the types of plots that you can have. There's a number that the ones that you're going to be using the most, of course, are the log plots, the shade. We have numeric, and you can plot the Earth model. That the Earth model is going to look blocky in this example, or what we call blocky is just, it's a piecewise discontinuous, is a bit more formal definition. The Earth model is constant in each layer, and then it can have a discontinuity when it goes across. And you're going to be able to manipulate the Earth model through the track display. We have an exercise after this on how to do that. You can add boundaries, you can shift them around, you can move the properties, and so on. And one specific plot that I don't think is used by anybody else, but this software, maybe I'm wrong, but people are not all that familiar with it. We have a vertical cross section, and this plot is, what this plot does is it assumes that the well is going around here in the very left, although you can change the radius. So at radius 0, you have the center of the well, and then you see the different invasion zones. So the very first one is the wellbore, then you have an invaded zone, and then you have you have the formation, the non-invaded zone in this case. Then after the track display, we have the Earth model builder that you access here, and we have it's a like I said, it's a set of modules. It's not a module on its own. It's not just one module. We have a module that allows you to detect boundaries. It's an old module, but it's been cleaned up and it works a lot better. But most of you are probably familiar with it. We have a module to populate properties, which basically turns logs into Earth model properties. It's the first approach you would do. We have a similar case, but for minerals. This is, I think it's been a year or two since we put that on. And we have a table view that allows you to see all the properties as numbers, as in a table. And then you can edit them right here. We have the well geometry tab that gives you, this is actually used some gives you detailed information on the inclination that you have. You can, in this example, I only have a number, but you can actually have survey data. And you would see here the bedding planes with the true and the relative azimuth that each one has. And we have the 3D geometry. And then probably the main Earth model module that we have is the compositional palette. I think this is very much UTAPWELS specific, which is where you have all the detailed information for each of the layers, the composition, all the petrophysical properties that you have, they're going to show up here. And now we have rock classes, which is a set of models that are associated to any layer. Those models can be resistivity, permeability, or effective medium theory, or NMR. And I think it's growing. It keeps growing. Every year we have something new. We also have the Earth model Petrophysical Calculator, where once you have set compositions, the main use of this is once you have set compositions, you're going to turn them into bulk properties, either using UTNuPro or SNUPAR for the nuclear properties. Then it can enforce structure consistency. This is something new, either Thomas Tiber structure or just making sure that the non-shell porosity is between 0 and 1. And you can also calculate effective medium theory if you want to do that, or NMR distributions. And then the calculations that you have in the right are not bulk calculations. They are assumed that you already have some properties, but they can also be very useful. So it's like permeability or resistivity, once you have water resistivity, porosity, and so on. Then we also have now some of the relatively new things. We have now ways to connect multiple wells, but at the same time keeping that connection local. So you can add formation zones, give them a name, and assume that in different wells you have the same formation zone. And those wells, you do not really have to give them it's not really connected through the 3D visualization. They do not need to have a specific location. We decided that we are a software that is very much focused on the well itself. So everything is defined locally, but they have a connection among different wells. But they still can have that connection. Then we have a number of log operations that you can do. One of the most common ones is to convert properties into logs. So the blocky logs that you saw, you can turn them into logs for either comparison within your own project, or if you want to export that to another software, that can be done here. And then we have log Petrophysical Calculator that basically does the exact same calculations that you were doing in the Petrophysical Calculator, but based in logs. So it looks very different because the logs have very different restrictions than the Earth model itself. We have a custom calculator where you can do simple calculations. You can do custom calculations for anything you have there. we have the depth shift. If you know how you want to line up different logs, you can do that here. You can stretch and squeeze, you can move it around. We also have the logs filter. This is a little underused because the industry just doesn't use it, because well, there's a reason why it's not so used. You're losing some information, but the cleanup that you get is very useful for some things. Like now that machine learning is super popular, it's getting rid of all the noise that makes your machine learning algorithm not work very well. So I think it's going to be more used. In this example, we're just getting rid of it's a low pass, so we're just getting rid of, it's a gamma ray log, and it's completely smooth out. Now, and then some of the most interesting things are, of course, the simulations. We have a number. We have the resistivity simulations. We're given a certain Earth model resistivity. A certain resistivity Earth model. We can generate the tool response. We have a number of tools. Some of them are 1D, some of them are 2D. We'll get into what that means when we talk about resistivity. And this is basically what it looks like. You have the blocky log is the resistivity. The red might be the noisier one is the field log, and then in green is what has been simulated, so you can see if you're matching or not. And very similarly, we have the nuclear logging simulation that has been updated very recently, so it's working faster and has more detail that it can take into account, and it even generates image logs for LWD. We also have an SP logging simulation. We have sonic logging simulations. And then we have a set of inversion modules. We have one for resistivity that is specific to resistivity for one of the simulators that was developed in-house for semi-analytic simulation. So it's only for 1D, but it works pretty well. Then we have the MCMC Inversion, which is probably the most commonly used software or piece of software besides the simulations themselves. This is the most common inversion strategy that users have. It works with as a Monte Carlo method, realizing the forward simulators that we already have. So it ends up being pretty accurate, and it can calculate uncertainties too. And then we also have the compositional joint inversion, where the end goal is to have the mineral or fluid composition plus porosity, water saturation. And we have a session on Wednesday on this one. It's relatively new, and we're still working on it. I mean, it's still working very well. It's already working very well, but Tianxin, who's the student that has been working on this, is still actively developing some strategies to make it go faster and be a little more accurate. And here, well, in this module, what we're trying to do is, we're trying to get the minerals and fluids, like I said, but the strategy is to match the properties that we already inverted for, while honoring some information, some prior information that we have from the field. And we have now that information can be set up either independently for each of the components that you have, or in 2D. We already have that. I didn't put an image here, but we have that. This is how it would look like. We're trying to match the blue, that is what we assume is the true Earth model for these properties, and we're trying to match it with a proposed composition. We have a long exercise here on Thursday. We also have the Sonic Studio that makes simulations of waveforms, giving a certain model that you may have. The tool can be defined here. And then you would get the waveforms, and then you can do some analysis. There's a number of methods that you can use to get the STC and the frequency dispersion analysis. You can see it's very high resolution simulation for Sonic. And we have even one that is even higher resolution coming, but that's still in the pipeline. This is already something you can use. I don't think we have any exercise for Sonic this time, but if you're interested, we can talk. We also have the NMR Studio that has been expanded the past 2 or 3 years. In fact, I think I have some outdated images, but we're going to have a long session about NMR inversions and trying to match actual. Now we have an NMR simulator, so you can actually match what you have, and it's a piece of software that has gone a long way. And we're going to have this Thursday, so if you're interested, come here Thursday afternoon. We also have the fluid flow simulator that does the invasion simulation as well as the formation testing simulation. We also have this on Thursday afternoon, and it's a little different because it's not really a tool response simulator like the others we were talking about, but this one is simulating the process of invasion, and then you can run the different simulations to test the different things. You probably saw on Monday we had a couple of sponsors were showing projects where they use this. Now well, this is how it looks like. We have 1D and 2D simulations. The end result is fully integrated with the Earth model. You can see it's easy to visualize. We've tried to make it as easy as possible to use, but as a difficult piece of software like it is, because it has a large number of inputs, it takes some time to getting used to it, but it works really great. So if you're interested in this, it's worth taking the time. You can define the tools. You have a flexible grid setup, and then this is something that people had been asking for a while, and we put it in 2 or 3 years ago. But now we've even expanded this. You can have custom PCKR curves, and now you can associate them to rock classes. We also and these are the results that you would typically get from the fluid flow. You would get a final Earth model that you can test the tools, and you also get everything in between. So for example, you can see how the pressure goes up and down in this specific simulation that was run. You can see water saturation, how did it process, how did it go on time. You can also see things depending on the radius, so the radial distribution for all these things, for pressure and water saturation and resistivity in this case. And you can see the same thing in the cross-section plot that we talked about before. This is where you would define your PCKR curves. It's not been updated. It was not updated this year, but some models were added to it. So, and as far as I know, it's working really well. We have more models than the ones I'm showing right now. And then you can input the data arbitrarily. That's something that people had been asking for a while, and I think there's a couple of sponsors that are using that. They have their own curves, field experimental curves. This is the same module you can use to compare how the curves look like in different conditions. Different layers may have different porosity and will show differently. Then we have the PTA type curve analysis also for pressure change analysis, for the result that you may have after your simulation. And then this is some of the newest developments. We have now diagnosis visualization plots. You can have box plots, you can have the multidimensional plots, and you can have cross plots that you can color and so on. And we developed them just recently, and we want to expand what they can do. We already got some feedback from the consortium meeting, but it'll be great if we get feedback here, a little more interactive feedback. We know they can be improved, and we'll work on that. And just to mention it, we have finally the Pore level petrophysics where you generate a certain packing, a grain pack. You voxelize it, and then you can run a number of simulations. You can also get data from CT scan and input it here. and then measure certain petrophysical properties. You can measure capillary pressure, permeability, conductivity, and NMR response. Other features, you can use an arbitrary unit system. You can record snapshots. This was something we developed, I think, about 5 years ago, where the software didn't have undo and you couldn't save. There were a lot of things you couldn't do. So because we wanted to keep it as usable as possible, people wanted to be able to keep a snapshot of what they were doing. So what we did was we just basically saved the entire project within the project, and you could reload it, and that's what snapshots do. But now that the software has gone a longer way, I don't think they're as used as before, because now you can save the visualization that you have. Now you can do undo. Now you can duplicate a well. So if you want to see, if you want to test multiple hypotheses, instead of going back and forth between snapshots, just generate 2 wells that have the same starting conditions and then go with that. But as much as I don't use them anymore, sometimes I'm surprised that people tell me that they're still using them. And once you get used to them, they can be pretty useful. And lastly, we have the TechLog plugin, where you can export and import data from TechLog. Well, and the very last thing, we can, everything that we do with UTAPWELS, we have a scripting interface, so you can interact with your data from MATLAB. You can get your data, visualize it, do anything you want with it. You can run the simulations. You can perform the calculations. Anything you can do with the user interface, or almost anything you can do through the user interface that is just manipulating the data, you can do it with through scripting. And that gives you a lot of power, because you can write your own workflows and reuse them. Or for example, we're going to have on Friday, we're going to have a sensitivity analysis case, which is perfect for scripting. Is the perfect way to do it. And this is just showing you how you can visualize your data. And that's it. I don't know if there's any questions so far. Make sure you unmute yourselves.
I have a question, Joachim. I don't really get it last year. What is the difference between normal resistivity inversion and MCMC? I mean, which kind of development? So is it only run faster, or how?
So the resistivity inversion module that we have works with the one that is not MCMC, works with it's a derivative based method. So they calculate the Jacobian, and then they do the inversion. It's fast, it's pretty fast, but it's only for the semi-analytic variant of simulators that we have. And the MCMC is more general. It's probably not as fast, but it's more general. So you can use it with any, and it's fast enough. It's comparable speed, actually. So in general, I think I would go with MCMC, because also if you want to use, if instead of using the semi-analytic, certain resistivity tools have the semi-analytic, some do not. So if you want to switch tools, you will have to use the MCMC. And it's not just for resistivity. The MCMC can also be used for nuclear simulations and for sonic simulations. So in general, I prefer to go with the MCMC, but some people prefer some people just trust more the Jacobian than the Monte Carlo case. Something else is that the MCMC will also calculate uncertainties, and which is something that the resistivity inversion by itself doesn't do. Last time I talked to David Pardo, who is the main, who has, his group is the one that developed this. I think they are putting it in, or they're in the process, and they might be able to calculate uncertainties at some point soon. But for now, in the version of the software that you have, MCMC can already do that.
Okay, great. Yeah, thanks.
Okay. I don't know if there's any other questions, comments. Okay. Well, if there's no comments or questions, let's take a 10 minutes break, and we're gonna come back. So yeah, we're gonna come back in let's say 10 minutes. Let me stop recording.